Here we have the three main drawings that I'm using in my research. Drawing number 18 shows the spring arms with weights attached and the rim stops as a linkage between the axle and the rim, turning only in the clockwise direction. MT25 shows 4 lever systems with weights. In quadrant 3, 1, 2, 3, for a clockwise rotation, the levers close in a scissor action. This swings down here and scissor closes, forcing the weight upward. At the 6 o'clock position, MT25 is the only drawing Mr. Bessler said should be studied extensively. In quadrant number 2, the 2 levers must bend slightly in, as you see here, not forming a straight line, but bending this way, in order to allow the levers to close at the proper point. A cord passing over the pulley connects the compound levers in quadrants 1 and 3 across the diameter. MT138, Mr. Bessler also emphasized the importance of this drawing called the toy page, and may give a clue as to the escapement needed for linking the axle to the rim. More on this later. The wheel is 40 inches diameter. The crossbar with adjustable length has 5 rim stops for clockwise rotation only. Simplified compound levers using only a 2-lever system and 4 weights connected via a cord across the diameter. A turnbuckle for adjusting cord tension, and the flat springs are shown. Why the long lever is limited in length. When it gets around to that position, and it closes. That's why it can only be so long. Show the primary weight is 108 grams and the shifter weight is 27 grams, only 9/10 of an ounce. It is the shifter weight that initiates a 90-degree movement and jerks the primary weight upward at the approximate 6 o'clock position. In this build, the movement upward is too late, more like 7 or 8 o'clock position, and a simulation may show how to change that. Having the weight fly up at a 6 o'clock position is essential for not spoiling the forward momentary crossbar torque. Here I show the travel stops. These are what prevent the levers from forming a straight line, and that would prevent the levers from closing here, so we have to have travel stops. There is a discrepancy where one half of the cycle is weaker than the other. caused by the cord having some slack or in tension, whether the cord loops over the top of the pulley or the bottom of the pulley. This is caused by the cord moving around the pulley is either in tension or it is loose. So when the cord is on the bottom of the pulley, it's loose, and when it's on the top of the pulley, it has some tension in it. So that can explain the discrepancy in the torque. The larger the pulley hub diameter, the greater this discrepancy. That's why the pulley diameter must be very close in diameter to the axle diameter. Both cord tension and spring tension must be carefully adjusted. This design favors a clockwise movement as shown. I'll show you what happens when we go in the opposite direction. You get none of that movement that we had before, which showed torque. This does not show torque, so this is a particular design which favors the clockwise rotation. Now we show the crossbar turning without springs with sound. Now we want to show what it sounds like and how it moves without the springs. It appears to be just a dead movement. Nothing special about that. And you can see by that movement that it lacks the aliveness when we install the springs. It's a dead movement. In the last picture of the wheel, we show spinning and show the 3-bob flywheel in the back, and each of those bobs can be adjusted in or out on the threaded rods for finally adjusting the balance of the wheel. Finally, I show the construction details. The wheel, a 40-inch diameter disc, is 1/2 inch thick, 9-ply, aircraft-grade Baltic birch, which does not warp. I gave it 2 coats of polyurethane varnish. The cross ribs are joined to the disc using truss head machine screws that thread into barrel nuts, giving great strength. The rim is 4 inches wide, 11 gauge, or 0.090 inches thick, soft aluminum, shaped with a sheet metal roller. The rim is made in sections that butt together with joints centered on a cross rib, using 632 by 1/4 inch long flathead machine screws, which are countersunk into the rim so that the rim has a smooth surface inside. The wheel axle is 3/8 of an inch drill rod, turning in flange mount ball bearings. I added a laser pointer to one flywheel spoke for accurately measuring angular displacement against wall, ceiling, and floor. Returning to MT138, I give my own particular interpretation of part of the drawing. B, from top to bottom, is the rim of the wheel laid out in a vertical line. Each of these blobs represents a rim stop, so that there are 5 on one side of the wheel face and 5 on the opposite side of the wheel face. This represents the pantograph here, shown in repetition, but it shows the alignment of the length of the pantograph with the rim stops here. And in doing so, if this is a correct interpretation, this gives us a way of automatically deciding on the dimensions of the pantograph based on the diameter of the wheel. This is one book that I recommend for anyone interested in gravitational theory, because it uses hydromechanical modeling to explain gravitation. This book is now available at Amazon.com for about $5.75, so it's a very interesting read, and I recommend it to you.